Hello everyone, welcome to lecture 53 in the course Diffusion in Solids. Today we are going to start talking about diffusion in very important class of materials which are semiconductors. So we will see some of the features of the diffusion in semiconductors in this lecture, and will continue talking further in the next video as well. So we know that the semiconductors are important for the microelectronic devices, for the gamma radiation detectors in several high frequency devices, and depending on the application, the material that you use are also different. Silicon and germanium are the most common ones, or some compounds like gallium arsenide, silicon carbide, and so on. So these are very the semiconductors is the most with so many digital revolution, electronic devices, and so on. Semiconductors are one of the most important classes of materials today. So these semiconductors, if we talk in this particular videos or discussions, we will focus primarily on the silicon and germanium diffusion. And these two elements, so for example, this silicon and germanium, they crystallize in the diamond cubic structure, whereas gallium arsenide, for example, crystallizes in a zinc blende structure, which appears like this. And here this table gives you the structure of some more elements which are semiconducting in nature, and the compounds also which are semiconducting, like gallium nitride, gallium phosphide, indium phosphide, and so on. So you can see that primarily they are zinc blende structure, pure metals are diamond, gallium nitride is woodside structure, and so on. And the band gap is also given, so some of them are indirect band gap, some of them are direct band gap semiconductors. Now you know that in the semiconductors, semiconductors are very sensitive to the doping. So the resistivity, so why we call them as semiconductors, their conductivity or the reciprocal is the resistivity is between the metals and the insulators. So the resistivity or the conductivity of the semiconductors is very sensitive to the doping. So a small amount of doping can cause orders of magnitude change in the resistivity values. So there are two types of doping, primarily N-type semiconductor, where N-type elements are antimony and which contributes one extra electron. So the concentration of the electrons is more in such semiconductors, whereas you have the P-type semiconductors where the concentration of holes is more. So for example, boron in silicon. Diffusion process are very important in several semiconductor phenomena. One of the example is shown here is a diffusion masking, where you want to basically deposit certain photoresist, let's say, on the substrate. Then you have to mask such that, and you want to basically ensure that it is only selectively deposited. So basically what you are trying to see is that you prevent the diffusion of, in this example, phosphorus to certain extent. So you basically can selectively choose your photoresist and such that the diffusion is inhibited in a certain regions. So like this, a lot of doping, for example, we will see that diffusion in semiconductors plays an important role. So before going to the diffusion in semiconductors, let us little talk about the defects. See, the defects in semiconductors are slightly different in terms of the energy and the concentration than in the case of what we saw in the metallic systems or metals. For example, silicon and germanium, if we focus on, they crystallize in diamond structure, which is having a coordination number of 4, and it has a lower packing density than in the metals, which is true. This is also true for the compound semiconductors as well. So, therefore, in the semiconductors, both vacancies and self-interstitials become important, because in an open structure, the vacancies and self-interstitials can be more easily accommodated. However, because the semiconductors like silicon and germanium have the covalent bonding between the atoms, the defect formation energies are very high. Okay. So, you can have the defect formation energies are higher in semiconductors because of the covalent bonding, and therefore, the concentration of the defects are orders of magnitude lower than in metals. So, on one side, now you have because, for example, in metals we saw that self-interstitial play a very negligible role when it comes to diffusion, except for the irradiation conditions. But in semiconductors, both vacancies and self-interstitials become important because of the lower packing densities. However, the covalent bonding in these semiconductors results into higher defect formation energy and lower concentration of the defects. In addition, what this figure also tries to tell, that in semiconductors the point defects can be either neutral or they can be in various electronic states. So, you can have the charged defects, charged point defects in semiconductors, which was not the case with the metals. So, point defects, because they introduce energy levels into the band gap, the charge of the defect is decided by the position of the Fermi energy level. So, you can have for example, the vacancies which are neutral, vacancies which are charged. Similarly, you can have self-interstitial which are neutral, which are charged. So, the total concentration of the defect at thermal equilibrium can be a summation of the various types of the defects. It can be charged, it can be positively charged, it can be negatively charged, it can be neutral, and so on. The concentration of uncharged defects is a function of temperature and pressure. But the concentration of charged defects is also a function of temperature, pressure, and the Fermi energy level, and Fermi energy level is changed by the amount of doping. So, in a way, the doping influences your concentration of the defects. For intrinsic, I mean for semiconductor, the product of N into P, which is N is the number of electrons, P is the number of holes, Ni is the intrinsic carrier density, and the N for N doping, as you increase the N doping, the negatively charged defects increase. If you have P doping, then the positively charged defects are more in number, and Ni is equal to square root of N effective C into N effective V exponential minus Eg by 2 kBt, where this represents the effective number in the conduction band. Here it is in the valence band. So, these are the effective densities of states in the conduction and the valence band, and as I said, Eg is the band gap of the semiconductor. For example, germanium has a band gap of 0.67 electron volt, silicon has 1.14 electron volt, gallium arsenide is 1.43 electron volt. There are two types of doping. One is the background doping, where there is a homogeneous distribution of the donor or the acceptor atoms, and these are the dopants which are introduced during the crystal growth. These are relevant for diffusion if the carrier density exceeds the intrinsic density. Then there is self-doping, which is also relevant for diffusion experiments or for of donor or acceptor elements. Diffusion becomes further complex if the concentration of indiffused dopants are high. Now, for semiconductors, as I said before, both vacancies and self-interstitials can play an important role for diffusion. So, if you write the concentration of self-interstitial Ci equilibrium is equal to exponential minus delta SIF into exponential minus delta HIF by kBt, and the diffusion coefficient can be written as Gi into A square Vi naught exponential minus delta Si m by Kb exponential minus delta Hi m by Kbt. So, delta Si f and delta Sim are entropies of formation and migration, and the delta Hi are the Hif and Him are enthalpies of formation and migration. The geometric factor it is equal to 1 by 4 in this case for the diamond cubic structure for the self-interstitials, and nu I naught is the attempt frequency, which is of the order of the Debye frequency. And the concentration of vacancy similarly can be written by this expression. This we have seen before also. The vacancy diffusion can be also written as similar expression, and as indicated before, this may carry charges. So, since the doping changes the Fermi energy levels, that they also in principle change the charge defect concentration and hence the diffusion behavior. Now, the total concentration of any defect like we saw before, the self-interstitial will be equal to the summation of each of the charged defect. And what is important many times is that this product, this is Ci equilibrium into Di, which is the concentration into the diffusivities. See, quite often it is not just sufficient to say that okay, if my self-interstitials concentration is low, then that means their contribution to diffusion is less. No, it is the product that we have to see, because if you have, let us say, a self-interstitial where the concentration is low but the diffusivity is higher, it may end up giving a lot more contribution to diffusion than simply reflected in its concentration. So, quite often we have to see this product which is Ci equilibrium into Di. Similarly, for the vacancies also Cv equilibrium into Dv. So, this product decides many times what are the contributions of a particular defect into the overall diffusivity. And the overall diffusivity, tracer diffusivity, can be written as Fi d star equal to Fi into Ci equilibrium into Di. So, you see the product is coming here plus Fe into Cv equilibrium Dv. So, Fi is 0.72 and Fe is 0.5. These are the correlation factors for the interstitial and the vacancy mechanisms respectively. Now, before going into more discussion, let me just give you some key features of the semiconductor diffusion. So, the shallow dopants like boron, phosphorus in silicon, arsenic, gallium in germanium, and zinc in gallium arsenide, they determine the conductivity of the material. The light elements like oxygen and carbon are the major contaminants and difficult to eliminate during chemical processing and crystal growth. In Czochralski grown silicon single crystals, oxygen plays a crucial role for impurity gettering. Some impurities introduce deep levels in the forbidden gap of the semiconductors. Such impurities are like gold in silicon are useful for effective electron hole recombination in fast switching devices. Another example is chromium, which is used for electronic composition of hard to avoid donors and acceptors in gallium arsenide. Fast diffusing metallic impurities are feared for their detrimental effects on device performance. Well-known examples are iron and nickel in silicon and copper in germanium. So, if the metallic impurity diffuses faster, it can lead to formation of certain phases and which can affect your device performances. So, without taking severe precautions, these metals are unintentionally introduced during high temperature processes. Then certain other metallic elements are deliberately deposited on semiconductor surfaces to produce ohmic or rectifying contacts. Sometimes you need to deposit these metallic elements. Diffusion of self atoms is the most basic diffusion process. That is true for any material. Therefore, its understanding is definitely important. The diffusion of hybrid solutes such as gold, platinum, zinc, iridium in silicon, and cadmium, zinc, and gallium arsenide can provide information on native point defects. Remember one thing, why this point has come here. When we talked about the defects in metallic alloys like vacancies especially, you have the experimental techniques to measure these defect concentration. Like we saw differential dilatometry, we saw the positron annihilation and so on. However, in the case of semiconductors, because the defect concentration is very low, it is very difficult to measure this defect concentration experimentally. So, quite often the techniques that we use for the metallic materials do not fare well in the case of semiconductors. So, diffusion actually gives a lot of insight about the concentration and the type of the defects. So, therefore, sometimes it is very important to study the diffusion of the hybrid solutes that provides the insights into the defect concentration and the defect behavior. So, the hybrid solutes are the ones which dissolve on substitutional as well as the interstitial sites of the host crystal, and their diffusivity usually in the interstitial state is much higher than in the substitutional state. So, this is important. Now people want to use also the computational tools to be able to predict and control diffusion steps for the design and development of the semiconductors. What are some of the challenges in the semiconductor diffusion? First of all, as I told, because of the covalent bonding, the higher formation enthalpies of intrinsic point defects such as vacancies and self-interstitial, and because of that, the concentration of point defects in thermal equilibrium are orders of magnitude lower than in metals. Then the open structure of diamond and zinc blende favors interstitial incorporation of self and foreign atoms, and therefore interstitial diffusion and interstitial substitutional exchange diffusion of hybrid solutes via the dissociative or the kick out mechanisms are more prominent in semiconductors than in metals. And here because besides vacancies, the self-interstitial can also act as diffusion vehicles. So, studying the diffusional process or analyzing them becomes more complicated. It is generally accepted that shallow dopants in silicon and host atoms exchange both types of intrinsic point defects. This so-called dual mechanism, as I told, gives a variety of complex diffusion phenomena. And the covalent bonding between the host atom limits the solubility of most foreign atoms to ppm ranges. This also implies that small amount of solute substance can act as inexhaustible diffusion sources. So, some semiconductor materials can be grown as single crystals with very high perfection. Dislocation densities vary from values as low as 10 power 3 to 10 power 4 centimeter square in gallium arsenide to virtually 0 in silicon. Germanium crystals with dislocation densities in the range of 10 power 3 to 10 power 5 centimeter square inverse are quite common. Then grain boundaries and dislocations which usually help attain equilibrium concentration of point defects are often absent. Then only free surfaces can act as sinks or sources for the annihilation or creation of point defects. So, in the polycrystalline metals, for example, you have the grain boundaries and dislocations, so that when you heat your material for diffusion and annealing at a certain temperature, you can almost be certain that you achieve the equilibrium concentration of the point defect. But because these are absent in semiconductors, that equilibrium concentration attainment is not guaranteed. Then surface reaction proceeding under certain ambient conditions may strongly influence solute diffusion. Oxidation, enhanced or retarded diffusion are well known examples. The crucial role of self-interstitials injected into silicon by the oxidizing SiO2 Si interface is a widely accepted example again. Now, let us talk about self-diffusion in semiconductors. It is much slower than what you see in the metals. For example, at the melting temperature, self-diffusion in silicon and germanium is at least 4 orders of magnitude slower than in metals. And this difference is due to the relatively large activation enthalpy of the semiconducting material. This is one example you can see between the log D and 1 by T, where this follows the Arrhenius plot, but the values of the diffusivities are much lower. Let us talk about few points on pure self-diffusion in germanium. This has been primarily measured by the radio tracer technique using isotope of 71 germanium or 68 germanium. These are the value of D naught and Q. Several researchers have tried, and there is a pretty close agreement between various measurements. Diffusion in germanium, self-diffusion occurs primarily by vacancy mechanism. People have also tried to study the isotope effects using 71 germanium and 77 germanium pair. Vacancy in germanium has an acceptor level in the lower half of the band gap, and hence it is a negatively charged vacancy. So you have the total tracer diffusivity is a sum of tracer diffusivity of uncharged vacancy plus the tracer diffusivity of negatively charged vacancy, and you can write the corresponding formula Fv into GV square omega V naught Cv naught equilibrium, where V0 basically represents the uncharged vacancies. Similarly, we can write this expression for the negatively charged vacancies as well. For the vacancy mechanism, as we saw before also, Fv is equal to the correlation factor is 0.5 and geometric factor is 1 by 8. So, omega is the exchange jump rates between tracer atom and the neutral vacancy. Similarly, for V minus, it is for the charged vacancy. We can also write for the non-degenerate semiconductors Cv equilibrium for to the ratio of Cv equilibrium for Ni is equal to N by Ni, where N and Ni are the free electron densities in the doped and the intrinsic material. So, N is here, for example, in the doped material, whereas here it is for the intrinsic material. So, you can also write then from these previous equation d star N by d star Ni. So, remember Ni represents the d star in the intrinsic semiconductor is equal to d star V naught by d star plus N by Ni d star V minus by d star. So, there is a linear dependence of tracer diffusivity on the ratio N by Ni. So, the more you increase this ratio, the higher will be the tracer diffusivity. The occurrence of additional charge states would lead to additional terms in this equation. So, for example, this is the expression where only the one negatively charged vacancy and the uncharged vacancies are present. Whereas, if you have more charged states of vacancies, then further terms will be added, which will be then in the ratio of N by Ni to the power R for acceptor level and Ni by N to the power R for the donor level. So, germanium self-diffusivity increases with N doping and decreases with P doping. The activation volumes, which talks about the pressure dependence, are usually low, which are 0.24 to 0.41 omega. These activation volumes are low because of more relaxed vacancies due to the open structure of germanium than the closed packed metals. And the positive sign of activation volume further supports the vacancy mechanism in the germanium self-diffusion. And the total activation volume is given as delta V into d star V naught by d star plus delta V V minus into d star V minus by d star. So, usually the activation volume for uncharged vacancies is more than the activation volume for the charged vacancy. For self-diffusion in silicon, the key challenge has been that the only accessible radioisotope is 31 silicon, which has a half-life of 2.6 hours, which is extremely less. Thus, the annealing time for diffusion measurements is hugely restricted, because if you go for a longer diffusion time, then you will have a lot of decay and the half-life correction becomes much more critical then. Then relatively large inconsistency in silicon diffusion data than germanium. So, if you see in certain papers, the comparison of silicon self-diffusion data is given across the different measurements by different research groups, and you will see that there is more scatter than what is observed in germanium. This is because of higher propensity of silicon to the oxygen. Is one of the reason that due to oxygen contamination during processing, or due to the implantation damage, or because of the very short half-life of silicon, these are some of the factors which can contribute to the relatively large scatter in the silicon self-diffusion data. It is generally written as 0.53 exponential minus 4.7 eV by kVt. This is from this reference. Then self-interstitial actually is the more dominant mechanism of silicon self-diffusion at higher temperatures. Particularly, the product Ci equilibrium into Di can be written like this, whereas for the vacancy mechanism it is given by this expression. Vacancy mechanism in silicon self-diffusion is dominant more at the lower temperatures, whereas at the higher temperature it is the self-interstitials. Whereas for the germanium, it is the vacancy mechanism which is the more dominant mechanism. So, we will talk about more aspects of the diffusion in semiconductors, particularly the foreign atom diffusion, in the next lecture. Thank you.